So we started our section on proof by induction, and we've seen a bunch of examples that are all sort of a similar style. We're trying to show that some equation is true for all n and n. Not all induction proofs are like that though, so I want to spend a little bit of time talking about some other sorts of induction proofs that you could see. So let's do an example here. We're going to show for all natural numbers n that 6 to the n minus 1 is going to be a multiple of 5. And just like before, it's going to be useful to try and convince ourselves that this seems to be true by looking at some cases. So this is sort of our P of n statement. That's our open sentence that we're trying to show is true for all n. So the statement P of 1 is going to look like, I shouldn't put an equal sign, it's not really an equal sign, is going to look like 6 to the 1 power minus 1 is a multiple of n. Multiple of 5. It's always 5. Yeah, 6 minus 1 is 5, and 5 is a multiple of 5. That's true. So the P of 2 statement would say 6 to the 2 power minus 1 is a multiple of 5. All right, that's 36 minus 1, which is 35. Yeah, 35 is a multiple of 5. That makes sense. You could do a few more examples if you want to make sure that this seems to be true. But I'm also going to go ahead and write what the P of k and the P of k plus 1 statement says. So P of k would be the statement, replace n with k, so this would look like 6 to the k minus 1 is a multiple of 5. This is what we're going to assume in our inductive step. And P of k plus 1 would look like 6 to the k plus 1 minus 1 is a multiple of 5. This is what we would be trying to prove in the inductive step. So let's go ahead and see how this falls out. We prove this by induction. Our base case is going to be the case where n is equal to 1. So for n equals 1, we have that P of 1 says 6 to the 1 minus 1, which is 5, is a multiple of 5. So the base case is true. Right, remember, the base case is usually pretty easy to do. The inductive step is where things get harder. So for the inductive step, we need to let k be some natural number greater than or equal to 1 and assume that P of k is true. So we assume that, remember what P of k said, it said 6 to the k minus 1 is a multiple of 5. Alright, let's try to unpack what that means here. To be a multiple of 5 means 5 divides 6 to the k minus 1. Right? It means that we can express, or we can write, that 6 to the k minus 1 is equal to 5 times some integer. Let's call that integer a, or some integer a. That's just what it means to be a multiple of 5. It means you can express that whatever that number is as 5 times some integer. Right? This here, right, this statement here, or rewriting it like this, that's our induction hypothesis. This is what we're going to need to use in order to prove, right, remember we must show P of k plus 1 is true. Okay, that is, we need to show that 6 to the k plus 1 minus 1 is also a multiple of 5. Now this is where things start to diverge a little bit, because in our last videos, the difference between P of k and P of k plus 1 was just sort of one extra term in an equation. You had like one long list of numbers being added together, and then here you had another list of numbers added together with one extra term at the end. This is obviously a little bit different than that. But in a way, these are similar because you've got 6 to the k minus 1, then you've got 6 raised to 1 more power, 6 to the k plus 1 minus 1. And so it might help to try and rewrite our induction hypothesis equation, moving that 1 to the other side of the equation. So by the induction hypothesis, we have 6 to the k minus 1 is equal to 5a. And we could rewrite that as 6 to the k is equal to 5a plus 1, just adding 1 to both sides. All right, now why did I do this? Because now that I have 6 to the k by itself, I'm able to multiply both sides of the equation by 6, and that's going to get me 6 to the k plus 1 power. Right, if I multiply 6 to the k by one more copy of 6, 6 to the k times 6 to the 1 would be 6 to the k plus 1. So multiplying both sides by 6 to get the following. We'll get 6 times 6 to the k is equal to 6 times 5a plus 1. That is, we get 6 to the k plus 1, right, because we can add our exponents together. 6 to the 1 times 6 to the k is 6 to the k plus 1. And distributing on the right-hand side, we'll get 30a plus 6. This isn't really exactly what we're trying to show here. Remember, we're trying to show 6 to the k plus 1 minus 1 is a multiple of 5. So I want to get a minus 1 over here. So let's just subtract 1 on both sides. And we'll get 6 to the k plus 1 minus 1 is equal to, I have to subtract 1 here. So this would end up with 30a plus 6 minus 1, 30a plus 5. All right, now this is starting to look like what we're trying to show up here. We've got 6 to the k plus 1 minus 1. We need to show it's a multiple of 5. Well, it certainly is, because we can factor a 5 out of the right-hand side. So let's rewrite this one more time as 6 to the k plus 1 minus 1 is equal to 5 times 6a plus 1. Now, since a is an integer, 6a plus 1 is an integer also. And so we conclude that 6 to the k plus 1 minus 1 is a multiple of 5, as we were trying to show. Thus, p of k plus 1 is true. And that completes our induction step. So now it's just a matter of wrapping this up by saying, by the principle of mathematical induction, we have 6 to the n minus 1 is a multiple of 5 for all n in n. This is a really sort of nice kind of proof. And it allows you to show something that's a little bit surprising. I mean, why does 6 raised to any power minus 1 always give you a multiple of 5? Well, actually, okay, there might be other arguments you could give here, but this same basic type of argument can really allow you to prove some surprising things. Now we're going to do another example, and this time it's going to be proving that an inequality is true by induction. All right, we want to prove that n squared is greater than 2n for all n greater than or equal to 2. Hopefully some alarm bells are going off for you, because this is the first example that we've seen where it's not for all natural numbers n, it's all n greater than or equal to 2. And so the key here is that this inequality is not necessarily going to be true for n equals 1. And so this just means that our base case is 2 instead of 1. Right? This time you've got your infinitely many dominoes, and you start by knocking over the second one in line. First one might not be knocked over at all. The first one might not be true, but all the rest of them are going to be true. So the induction argument is going to follow it the same way. We just start with a base case of 2 instead of 1. All right, now let's think about what this statement says for some small cases. P of 2 says that 2 squared is greater than or equal to 2 times 2. Okay, 4 is greater than or equal to 4, that's correct. P of 3 would say 3 squared is greater than or equal to 2 times 3. 9 is greater than or equal to 6, that's true. P of 4 says 4 squared is greater than or equal to 2 times 4. Okay, 16 is greater than or equal to 8, sure, that's true. And P of k would say that k squared is greater than or equal to 2 times k. P of k plus 1 would say that, okay, replace n's with k plus 1's, so k plus 1 squared is greater than or equal to 2 times k plus 1. So this is what we're going to use in our inductive step. Let's go ahead and see if we can prove this. We'll prove this by induction. Our base case is that n equals 2. We have that the statement P of 2 says that 2 squared is greater than or equal to 2 times 2, which is true. So our base case is done. Okay. Now for our inductive step, we now need to let k be some natural number greater than or equal to the base case. Usually we'd say greater than or equal to 1, but our base case isn't 1 here, our base case is 2. So we'll let k be greater than or equal to 2 here instead, and assume p of k is true. That is, we're going to assume that k squared is greater than or equal to 2 times k. All right, this here, this is our inductive hypothesis. This is what we're going to need to use to show that p of k plus 1 is true. We must show p of k plus 1 is true. All right. So I want to actually pause the video now and give you a minute to try and puzzle this out, right? So this is what we're assuming up here, and this is what we want to show. So just like before, we really need to try and manipulate this in some way to get it to look more like this, right? To be able to let us conclude that this is true. So I'm just going to pause it, and I'm going to, well, actually maybe you should just pause it yourself so I don't have to do a whole new video. Pause it and see if you can figure out how to do this algebraically, and I will continue shortly. Okay, so this is continuing. I hope you've paused to try it yourself. We want to show that p of k plus 1 is true, which means we must prove that k plus 1 squared is greater than or equal to 2k plus 1. So I'm going to rewrite that as 2k plus 2, just distributing that out. And I'm also going to go ahead and distribute the left-hand side to rewrite this as, if I squared this, I'd have k plus 1 times k plus 1, which is k squared plus 2k plus 1. All right, this is what we need to show. I'm just going to sort of put a box around this and say, need to show. Okay, so we know that this is true. We want to show that this is true. So by the induction hypothesis, we know that k squared is greater than or equal to 2k. Okay, now we're trying to show that k squared plus 2k plus 1 is greater than or equal to 2k plus 2. Well, what's the difference between sort of the left-hand side here and the left-hand side here? Well, we've just got an extra 2k plus 1 here. So let's see if it helps to just add 2k plus 1 to both sides of this inequality, which we know that this inequality is true. So adding 2k plus 1 to both sides gives us k squared plus, I'll just do it in a different color, 2k plus 1 is greater than or equal to 2k plus 2k plus 1. All right, now this is sort of what we want on the left-hand side, right? We're trying to show that this is true. So all we really need to do is show that this right-hand side, because we know this inequality is correct, so we need to show that this 2k plus 1 is in fact greater than or equal to 2k plus 2. If we can show that this is greater than or equal to 2k plus 2, then we'll have that this inequality must be true as well. So why do we know that 2k plus 1 is greater than or equal to 2k plus 2? Well, notice that since k is greater than or equal to 2, that was our assumption up at the top, that was our base case, we have, right, we're trying to show 2k plus 1 is greater than or equal to 2. So we would have that 2k is greater than or equal to 4, and 2k plus 1 is going to be greater than or equal to 4 plus 1, or 2k plus 1 is greater than or equal to 5. So in particular, we have that 2k plus 1, we have this right-hand side here, let me rewrite it in red just to be clear what I'm talking about, is going to be greater than or equal to 2k plus 2, what we have here. Okay, because 2k plus 1 is greater than or equal to 5, so it's certainly going to be greater than or equal to 2. Actually, it'll be strictly greater, but we don't even need that. So we can conclude that k squared plus 2k plus 1, the left-hand side here, is greater than or equal to 2k plus 1, which in turn is greater than or equal to 2k plus 2. And this inequality is what we're looking for. Thus, p of k plus 1 is true. And that means that by the principle of mathematical induction, n squared is greater than or equal to 2n for all n greater than or equal to 2.